Hello everyone. So in today's video, we're going to cover chapter 6, and it really explores periodic trends across the rows and columns of the periodic table in terms of radius, ionization energy. So we'll be covering that, and then we'll talk a little bit about lattice energy. Okay, so first just take a look. Take a moment to just look at this picture here of atomic radii. What this is showing is basically the radii of the atoms. So these are in picometers. So hydrogen here, 53 picometers. And as you go down, notice what sort of trend that you observe. You can just focus on first the main groups, so not the transition metals, but notice the size of the atom as you go down. The radius is determined by the center of the atom to the outermost point of the atom. But basically notice the trend, form some idea of what you think the trend is, and then also let's go and look left to right. Do you notice a trend there? Is something increasing or decreasing here? So we could start here, even going across the transition metals all the way across. What do you notice? So hopefully, first of all, you should have noticed that the size increases as you go down the periodic table. Why might that be? Here, hydrogen is very teeny tiny. As you go further down, lithium is quite a bit larger, sodium, potassium, etc. If you notice, cesium is the largest. On this side of the periodic table, we have helium. Also, fluorine here is quite small. As you go down, you're still seeing an increase. So hopefully something has come into your mind about why that is. Basically, if you recall just from working in our previous chapter with different shells, different n levels, as you go down the periodic table, you're adding more levels. So for example, if we just focus on the S block, we're going from an n equals 1 to n equals 2. So these are larger and larger shells. So you're literally adding more electrons to these atoms, and those electrons need to go someplace. So as the lower energy shells start getting filled up, you have to go to the next level, so bigger and bigger. So size increases as you go down because n increases. What about when you go across the periodic table though? Hopefully you notice that the size decreases. But why might that be? You're adding more electrons, right? Every time you go to the next element, you add a proton, neutron, and electron. So you're adding more electrons. So why doesn't it get bigger? Are you adding more n levels? Here you're not. You're still in n equals 3, which is for the S block, that's still 3s. Here is still 3p. So you're still in that n equals 3 shell. But what else is increasing? And I kind of gave it away there a little bit. If you caught it, you're adding more protons. So as you go across the periodic table, yes, you're adding more electrons, but it's still in the same level, but your number of protons increases. So what does that have to do with it? So basically, you have a lot more positive charge in the nucleus. Is that going to attract the electrons more or not? It's going to attract. So it's basically like pulling on those electrons more. As it pulls on the electrons more, it brings it closer to the nucleus. That's why it constricts the size, and that's why you see a smaller radius as you go across. Okay, so for the main group, I need you to know those two key pieces. Atomic radii increases as you go down because of increasing n, and it decreases left to right because of increasing z. Don't forget what z is. Z is atomic number, so that tells you the number of protons. So as we increase the number of protons, you're increasing that attraction of that electron. In the transition metal, you don't see as dramatic a change. Something is happening. As you do go left to right, you are increasing the number of protons, but that's kind of counteracted by something else. You're actually putting electrons in the D block. So D blocks actually are going to shield. And just if you recall, we're starting D here at 3D. So You go 4s3d, you're starting to add electrons into an inner level. So it kind of shields and blocks that positive charge more. So basically, electrons are not feeling that full Z. We call that Z effective or ZEFF. So it just basically cancels out. As you go down and you get into this lanthanide series, actinides further down, you're starting to add into F orbitals. So going down, we would have expected, oh, we're adding into more N's. We're going to make the atom size larger, radii larger. But what ends up happening is you're starting to fill into F orbitals as you get down here. And F orbitals, if you remember the shape, it's similar to D, but more lobes, more complex. And most of that electron density is outside, away from the nucleus. So you actually have very poor shielding, meaning you're letting more of the plus charge be felt. So those electrons, even though they're in greater N levels further out, they're being attracted more to the nucleus, so it constricts them. So basically, this also counteracts that effect. So very little change here. I'm more concerned with you guys knowing the main group trends and the reasons why. Okay, let's talk about ionic radii. You guys have already had experience with ions. When you lose an electron, you form a cation. When you gain an electron, you form an anion. So look at this picture here. The parent is just the neutral atom. So for lithium, Li is the neutral parent. Li plus is the cation. Notice the size. These pictures represent the different sizes here, quite a bit smaller. So for the cation, you're seeing a lot smaller size for the cation versus the parent. What do you notice for the anions? Obviously, you're going from something neutral to an anion, and look how much larger it is, just based on the pictures that I'm showing you. And there's some data here. These are in picometers. Why is that? So for the cations, what I want you to think about is, first of all, what's happening? You're removing some electron, right? 1, maybe 2. For a group 2, you'd remove 2 to get to magnesium 2+, for example. Where were those electrons? So let's focus on lithium. Lithium has a Z of 3, atomic number 3. So in a normal situation, 3 protons, neutrons, and electrons. Where do they go? Those first 2 go into N equals 1, specifically the 1s orbital here. Then that's full. So then you need to go to the next level, N equals 2. So it's in a 2s. So a neutral lithium has electrons. The outermost electron is in a 2s. The reason why lithium actually does form a cation is because this is further from the nucleus. It could be removed a little bit more easier than these inner ones. But also, if you remove it, you get back down to helium, the previous noble gas, which is a stable electron configuration. So notice, you go from something having electrons in an N equals 2 level to now only having electrons in an N equals 1. Just take a step back and just look at those pictures. Hopefully you can see that this is quite a bit smaller than the N equals 2 version. Okay, the anion one is a little harder to visualize, but what you need to know is anions are bigger than their parent, and atoms actually swell when they get more electrons. You could think of it a little bit more, there's more repulsion, they're swelling a little bit there, but also when you add more electrons, they're not feeling as much of that positive charge if there were less electrons, meaning they're sharing that positive charge more, so they're not feeling that constriction towards the nucleus as much. So it ends up creating a situation where the atom swells or gets larger. Okay. The next topic here is ionization energy. So this is something you guys have already conceptualized. It's the energy to form a cation. And it's specifically the energy to rip out an electron from the nucleus. So it's defined in a specific way. It's the energy to remove 1 mole of electrons from 1 mole of gaseous ions. So just in this example here, if I'm just looking at sodium, removing an electron, and we write it like this, to show electron is a product. It's lost as a product. And there's an energy here. This requires energy, and hopefully that's intuitive to you, because if you're going to pull an electron away from the positively charged nucleus, that's going to take a lot of energy. That electron Ed is already attracted to its proton Penelope plus attracted to minus. There's a strong attraction there. And then to rip it out, you need to add energy. So this is the first ionization energy for sodium. You could try to remove another electron. For example, for Na+, you could try to remove one more and get Na2+. That actually requires a tremendous amount more energy, so that doesn't happen. That happens when you get into situations where you have like a group 2 element, and the magnesium, the first two are a little bit easier to remove. So just in general, if the ionization energy is low, and this is a low number, as you can see, a group 1 metal does like to form a cation, then a cation will form. So I give E sub I as ionization energy. Sometimes it's labeled IE. So here's a trend of the ionization energies across the periodic table. So I'm going to go hydrogen to helium, and then lithium across the periodic table, then sodium across the periodic table, etc. Okay, so this is what you want to focus on here. Ionization energy starts here on the y-axis at 0 and increases. So the peaks are where you have noble gases, and hopefully that makes sense to you. It's hard to rip out an electron from a stable noble gas configuration. It either has its full ideal duet or octet. But if you start at a row, like say group 1, lithium, sodium, potassium, these are low ionization energies. And it increases, in general, the trend increases as you go across. Why is that? So the main reason why is it tracks with atomic size. We just talked about the atomic radius being smaller as you go across because there are more it's feeling more protons. You're adding more protons. So basically, you have greater number of protons in the same level, and it's feeling more of that positive charge. So as you go across a periodic table, it's going to be held on more tightly, and it's going to be harder to rip out and pull an electron out of the atom to create a cation. So hopefully that makes sense. As you go across, there's more of an attractive force. You cannot rip out that electron as much. So overall, it increases. But look at these little blips here. We call these anomalies. Why is there this dip at boron and then also at oxygen? We're going to take a look at why that is. So this is the same chart. Here, I'm just showing it should be increasing steadily as you go up, but we see this dip at boron. I'd like you guys to just pause and take a minute and think about why that might be, and look at the electron configuration. Don't look at my answers right now. Don't look at this left side of the slide, but just draw out an electron configuration and partial orbital diagram to explain why it might be easier to remove the outer electron of boron versus beryllium, and why it might be easier to remove the outer electron of oxygen versus nitrogen. So pause and think about that and then come back. Okay, so if we look at the electron configuration of boron, we have helium, a 2s2, 2p1. So let's just back up. Lithium has the 2s1. That's easy to remove because it brings you back to, that's an outer electron in a 2s, and it brings you back to that ground state of helium. Beryllium is a 2s2. That's harder to remove because, number one, you're adding another proton. You also have this filled subshell, a 2s2 orbital. Boron, though, we're now adding an electron to the 2p orbital. So the 2p orbital is now its outermost electron, and a 2p is different than a 2s, right? How are they different? Which one's higher in energy? The P is, because it can't penetrate as close to the nucleus. The P is that infinity lobe. So the electrons are further from the nucleus, meaning it's easier to pick off. It has higher energy. It's not as stable as that 2s electron, so it's easier to pick off, easier to remove, hence the slightly lower ionization energy versus beryllium. Okay, let's take a look at oxygen. Before oxygen, though, we had nitrogen, which was a 2s2, 2p3. When you add the fourth p electron to oxygen, you get this electron configuration, where first of all, nitrogen just had 1, 2, 3 here, but the fourth electron doubles up. And so you have this paired orbital here for oxygen. So the reason why this is easier to remove is when you remove this versus one of these guys, you're relieving repulsion. So as a last resort, you want to double up, but if you have to, you have to. The reason is you want to minimize repulsion when you follow Hund's rule. So that's why this is easier to remove. It's higher in energy because it's paired here. Removing it relieves repulsion. That's a little bit more energetically favorable. That's why it's slightly easier to remove an electron from O than it is for N. Okay, as I mentioned before, you can remove more than one electron from an atom. We call these successive ionization energies. So sodium, if I remove the first one to give Na+, that's easy, that's in the 500 range. But if I try to remove a second one, and these are all the successive ionization energies to remove the second or third or fourth, that requires about 10 times as much energy. That's why that doesn't happen. It's so hard to do. So what that means is the ones that are easier to remove are these outer electrons. Once you start getting into a core noble gas electron, those are way harder to remove. For magnesium, it's a group 2. So you can see that 2 are relatively easy to remove. And then you get this huge jump here because the next one is trying to remove a noble gas. So you can actually look at successive ionization energies. For example, silicon. If I saw 1, 2, 3, 4 are easy to remove, and the next big jump means you had a noble gas electron you're trying to remove and doesn't want to happen, that means that element had 4 outer electrons. It must have been a group 4 element. The opposite of ionization energy is electron affinity. So this is just energy to add a mole of electrons to a mole of gaseous atoms or ions. So that's just basically forming an anion. Now here we have the electron on the reactant side because you're adding it to form the anion. These are all going to be negative. Hopefully that makes sense to you, because when an electron is added to an atom, it now feels that electrostatic attraction with the proton in that atom, and that releases energy. So if the electron affinity is very highly negative, an anion will form. You know that halogens like to do this. Group 6 also likes to do this, even group 5s, forming nitride and phosphide, for example. So there's no real trend. I need you to know this is a chart of electron affinity. It's a little different. It's putting more negative up. So that means these want to form anions. So not surprising, these are your halogens. And then the next levels are further down. The next other groups to the left on the periodic table are further down. Okay, so just to kind of wrap things up, basically group 1A and 2A, they have these s outer electrons. Group 1 has an electron or valence or outer electron, just one of them in that s. Group 2 has 2 electrons in the s. So these guys will tend to lose their 1 or 2 electrons to go to the previous noble gas configuration. That ends up giving them that noble gas configuration. And a lot of times what we call that is the octet, just because unless it's helium, that outer next shell will have that full octet, 8 electrons. Group 7, which are the halogens, they have this generic S2, but P5. So they're just one electron away from gaining that noble gas configuration. So these guys will tend to gain one electron to get to P6. So we've mainly been talking about these guys adding or gaining electrons to become ions. But something that can also happen is that they can share electrons, and that's how we get bonding. For example, hydrogen has a 1s electron, and it will share with another H, 1s, to form a bond of 2 electrons. And that allows it to obtain that duet that's necessary. 2 halogens can also share an unpaired electron to get its octet. So later on, we're going to be building molecules and creating bonds with molecules. And what we're going to be able to do is form molecules so that they do have 8 electrons around them. That'll help us build. One of the last sections I want to talk about is just forming ionic compounds, energetically, why that happens, and what's lattice energy. So if we form a cation from lithium, that takes energy. You know that. Ionization energy, you got to rip an electron from that positively charged nucleus. To form an anion, that releases energy. So what I want to look at is forming lithium fluoride, which comes from lithium plus and fluoride minus. If I do each of these steps, overall, this is positive, and this requires energy. So forming the ions overall requires energy. So why do ionic compounds form at all? The reason is because when they actually come together, when the anion and cation find each other, come together, energy is released in forming the ionic bond. So it all comes down to that key step of the electrostatic attraction. So when once you form the ions and they find each other and they form that ionic bond, then you release a boatload of energy, minus 1,050 kilojoules. There's some language you need to know that's called lattice energy, and the lattice energy is actually the opposite sign of this. So it's defined as the energy to break apart an ionic bond. So if I just take LIF and I break it apart, that costs energy, so it's just a positive of that number, and it's given delta H lattice. Just remember that anytime you break a bond, that's always endothermic because you're ripping apart an electrostatic attraction, some sort of plus and minus. For ions, it's cation and anion, those real ion charges. You're breaking that. For a covalent bond, it's the positively charged nucleus attracted to the electrons of the other guy. You're breaking apart that. So in all those cases, delta H is greater than 0. That's endothermic, requires energy. Something else you guys need to understand about lattice energy is that it's proportional to the charge of the ion. So hopefully you can think about other types of ions combining, so not just plus and minus, but maybe 2 plus and 2 minus. The greater the charge, the greater the electrostatic attraction. And the reason is those ions are held more tightly. Those charges have a stronger magnitude. So what happens is that lattice energy is greater. It's harder to break them apart. That's why some ionic compounds don't dissolve in water. Those new water ion solvation energies that are released aren't even enough to counteract the breaking apart of some of these really strong lattice energies. Okay, the other thing that can affect lattice energy is smaller ionic radii. If the ionic radii is smaller versus some other compound, those ions can actually get closer together. So if they get closer together, they feel that greater electrostatic attraction, so the lattice energy is greater. Okay, that is where I'm going to end today. And in the next section, we are going to start talking about covalent bonds, and we're going to finally be able to build molecules. We're going to draw structures, and then we're going to start thinking about molecules in 3D space. Okay, I will check in with you guys later.